Okay, so we are going to talk about infinite series in this video. So to introduce this idea, first we need to talk about sequences. So a sequence would be just an ordered list of numbers like 2, 4, 6, 8, 10. So sequences can either be finite or infinite. So finite would be like I end the sequence at 10, and infinite would be I put a ... to indicate that the pattern is continuing. So a series takes a sequence and then just adds up the terms. So really all a series is adding up the sequence. So it's going to be 2 plus 4 plus 6 plus 8, so on and so forth. And you can indicate that this just keeps going for forever with that plus ... and that means that we're just going to keep adding up the terms. So what's interesting is that once we get into series, we get very interested in understanding both a finite series and an infinite series. The two things kind of are a little bit more interlinked than, say, like a sequence would be. So finite series, of course, is referring to just adding up a finite amount of terms, so 2 plus 4 plus 6 plus 8, versus an infinite series would be that we just keep adding up the terms for forever. Now, like I said, in a sequence, usually we don't flip back and forth, but when we talk about infinite series, we very often will investigate finite amounts of the series to see if we can make some understanding or get some sort of greater understanding about the infinite series. So these two concepts are actually kind of closely intertwined. So one of the things then that we really have to understand and discuss is notation for summing up the first n terms in a series. So using the same sequence that I keep referring to. So say like the first term, if I only wanted to sum up the first term, that would just be the first term, so that would be 2. The second the next two terms, so that would be the sum s sub 2, and then I would add 2 plus 4. Versus if I have s sub 3, so now this is indicating that I need to add up 3 terms, 2 plus 4 plus 6. And so if you wanted to add up, say, n terms, the way that you could do that is you could have the first couple terms, 2 plus 4, a ... and then you could have a formula for what those nth terms look like. So this is one way to represent a sum of n terms, but there is another way that we can sum up n terms, and that is by using what's known as sigma notation. So hopefully you're familiar with sigma notation, so sigma notation looks like this. We use the Greek letter sigma, so it's not like a messy looking backwards 3. It does have kind of these nice sharp corners, so you just do want to practice making clear looking sigmas, just advice for you. And then when we have sigma notation, we also have kind of these signs here. So this is talking about k equals 1 to n. This is where it starts and where it ends. And so then instead of writing out the terms like 2 plus 4 like we have here, we just straight up write out the formula for each term. And so then if I were to write this out from 1 to n, I would get the exact same sum that I had before. And this does just bring me to just a general note about series notation. So you're going to see this a lot when we talk about infinite series. So series notation in general kind of looks like this. And so the a sub k, so if you see this just stands for a formula for terms. So we can refer to the general idea of a series and just write a sub k here, or we can write in an actual formula. So if you look at what I did here, right, I wrote in the actual formula. Here is the theoretical formula. And then this part here, so again, this is that start and stop. So this is what's known as our index. And it's actually possible, depending on kind of what we're doing with it, we can kind of play around with these different pieces of the notation. But series notation, this is really essential when we're talking about infinite series or finite series. And so if there's an n here, that means that this series ends at the nth term, which would automatically make it finite. Okay, so now let's examine the partial sums of a different series. So let's change to 1 plus 1/2 plus 1/4. So we'll really use 1 over 2 to the n minus 1. So we're going to evaluate these partial sums. So the first term, right, is just 1. So that sum is just 1. So the second partial sum is going to be 1 plus 1/2 using our formula. So that'll give me 3/2. The next term will be 1 plus 1/2 plus 1/4. So that will give us 7/4. And so then if I keep adding up the first n terms, and sorry, I'm missing a 1 here. There should be a 1 here. So if I keep adding up the first n terms, so the question is, how could I determine what the value of this sum actually is once I get to like an nth number of terms? Okay, so let's now kind of appreciate where we're going with this right now. I have started by looking at sums and just kind of seeing what they add up to. And we're trying to see if there just comes a point where I can maybe summarize what the sum comes out to. So how do we do this? Well, one way that we could potentially do this is we could think of another way to view this sum. So instead of having to go through and add up like all these different terms, like this is a lot of work, right? Once we get to like the fifth term, right? This is a lot of stuff to have to try to add up. The question becomes, is there some other way that I could get to this value without having to add up these terms? And so it turns out that there is. So actually, this could be a great question for you if you want to think about this for a minute. You could pause and just try to like see if you could figure out what is an alternative formula of how to figure out what this sum will be without having to add up a billion terms to get to it. So I'll tell you what the formula is. So it's actually just 2 minus whatever term that we're on. So it's going to be really 2 minus 1 over 2 to the n, 2 to the n minus 1, sorry. So just appreciate the sum for right now. I'll write it out in a moment. So this could be represented as 2 minus 1. This could be represented as 2 minus 1 half. This could be 2 minus 1 fourth. So if I want to get to what that nth sum is, well, now instead of having to like fret about, oh gosh, how do I add up these nth, like these n terms? This seems like a lot of work. Well, if I view the partial sums this way, this actually isn't too much work, right? So in this case, this would just be 2 minus 1 over 2 to the n. So there is like this really clear pattern here that we can kind of play with and say, okay, that would actually be the value of this particular sum. And now that I have this formula for this, I can also write like out an easy formula for this. So I could write out, I could instead get a common denominator here and just write a formula for this would be 2 to the n minus 1 over 2 to the n minus 1 over 2 to the exponent n minus 1. So this would be an alternative formula. These are actually equivalent formulas to one another. But this is kind of an interesting thing that can sometimes be done. So some partial sums have this nice, clear formula with them. So is it always going to work like that? No, but it's interesting when it does work like that. And the other thing that is kind of like, there's kind of a lot going on here. So these partial sums by themselves, these are technically also their own sequence, right? So you have kind of built into this, right, a sequence of sums. So if you have a sequence of partial sums, the way that we could represent that is just S sub 1, S sub 2, S sub 3, where each one of these stands right for its own sequence of sums. Now, when we have a sum that does not end, so far we've just been looking at finite sums. So when the sum doesn't end, we call that an infinite series. And the infinite series uses the same index notation, but instead of having an n here, we put an infinity symbol here. And so yeah, so this indicates then that I am just going to continue this on for forever. But like I said, so there does come a point though where like with some of these, depending on what the partial sums look like, some of these infinite series may actually converge to a particular number. So very often what will happen is to investigate an infinite series, we might investigate also a finite series associated with it. So just remember, we have an infinite series which can go on for forever, and then we have a finite series which can go from 1 to n. So sometimes, like I said, the partial sums in an infinite series can converge to a value of L. So if we go back just for a second, so if we just think about like what's going on with this sequence, so if I know within this sequence of terms that I can rewrite my sum like this, well, as n goes to infinity, what is the value of this? Well, ultimately, if n is going to infinity, right, the value of this fraction will end up going to 0. And so you can kind of start to see like, okay, in this particular instance, it seems like there comes a point where, yeah, I'm adding on these terms, but these terms aren't really adding anything else to the sum. And that's very interesting when that happens. So there is going to be this connection between infinite and finite series. And what we get interested in is when those partial sums converge to some value L. So when that happens, we write that the infinite series equals L. And so then we'll say that either the series converges to L or we'll say that the sum equals L. So either way. Okay, so this is what we will be examining in a lot more of this series. Okay, so I have a whole bunch of videos on all of these topics, and we're going to break down different ways to understand this because it seems really complicated when we're looking at it versus at partial sums. But a lot of these infinite series are just going to have different tips and tricks of how you end up evaluating them. Now, one other way that we can think about partial sums actually is with area. This is another very interesting thing to kind of think about. And this can be another way for us to like kind of see more clearly what is happening. So let's say that I want to use a sub n equals 1 plus 1 over n. So I want to sum up this sequence. Okay, so let's talk about like how we might do this. So first I can look at the partial sums. So if I wanted to sum this up, so for my first one, I'd have just 2. And then for my next sum, so here's my first term, here's my second term, this becomes 2 plus 3 halves. For my next one, I add up these 3 terms, so I have 2 plus 3 halves plus 4 thirds. Okay, so I haven't even added the value of these, but I just kind of want to figure out like what is going on with this particular sum. So if we want to use rectangles to figure out what's going on, what we're going to do is our rectangles are going to represent just the newest addition to the sum. And then let's just look at how that's going to pan out or how that's going to come together. Okay, so the first term was 2, and then I added on to it for h sub 2, I added on 3 halves. For the next one, I added on 4 thirds. And so we can see a pattern, right? So the next one I'll add on is 5 fourths, then 6 fifths. But eventually over time, like as we continue to add on more and more terms. So if you think about what's happening here, right, there comes a point where this 1 over n, right, this is going to start to get very close to 0. And so if you look at what's happening here, eventually these terms that we continue to add on, they're basically going to just be adding on like a 1, right? Like 1-ish. It's going to be just a little bit over 1. It's at some point n gets large enough where this effectively just becomes 1. So you can see that this sum, though, over time, so if I add on an infinite number of terms, you can also see what's going to realistically happen with this, right? Because I am adding on a minimum of 1 to each term, and so it becomes really clear, could this possibly converge to a single number? No, you can see that we're adding on a certain amount, so it's just going to continue to grow infinitely. So rectangles are an interesting way to kind of think about how these sums are working. Versus, let's compare this to 1 over n squared. So I'm not going to write out the whole formula this time. You kind of get the idea behind this. So the first term is 1. And then the next part that I would add on to that would be 1/4, and then 1/9, 1/16, 1/25. So very quickly, these like fractions get really, really tiny. And eventually, these sum terms, right, they just start going to 1. So again, if I'm interested in could this sum converge to something, this feels more realistic because at some point we're just adding on 0 effectively, right? So rectangles can be a very interesting way to wrap our head around, could an infinite series converge to a particular number? And so yeah, so this is going to basically 0 at some point. So the only thing I really wanted to press upon in this video is this idea of how sums can grow or not grow and how we might break that down. So in other videos, we're going to break down how to determine if a series converges. So we're going to have a whole bunch of different methods to help us figure that out so that we don't have to sit there and mess with these little sums or making these rectangles. There's actually a lot of different methods to do this. So I'm going to leave it at that, and we will talk way more about other techniques for this in other videos. So I will talk to you guys in another video. Bye!